In problem 15, we're given a box that is in between a parallel plate capacitor. As we know from chapter 27, a parallel plate capacitor is simply two oppositely charged plates. This simply means that their charges are going to be going the same way ultimately. So if we just draw the electric field lines of the parallel plate capacitor, positive charges, as we've learned before, always point outwards and away from here. And because it's a plate, it's going to point up towards the negative plate and through the box. And with the negative charge, they always point inwards. So going to be pointing into the plate and again through the box, pointed in the same direction as the positive electric field lines. So if we just draw these electric field lines through the box, the charge is going to go in the box and then it's going to flow out of it. And as we talked in lab, flux is just the flow of the electric field. And Gauss's law is all about what the flow is of certain problems. So this problem just simply asks for the net flux of this box. This box is a 1 by 1 centimeter by 1 centimeter box. And they give us the electric field strength, but ultimately we really aren't going to need to know that, because if we look at Gauss's law, which is the electric field vector times the ds vector, which is just simply the surface area, it is equal to the enclosed charge of the Gaussian surface over epsilon naught, which is just a constant. If we look at this, we can draw a Gaussian surface in here, but it's just going to be a cube just like the object itself. So it's almost just easier to look at the object itself, but we'll draw a little Gaussian surface in there. But that's our little cube. The charge of the electric field is going to go in, it's going to flow into the bottom of the box and then out of the box as well. So that's ultimately going to end up in a zero charge. So if the enclosed charge is zero, because none of that charge is actually being enclosed, we're going to see that that becomes 0 over E epsilon, which ultimately just equals 0. So we can see that the net flux is actually just going to be 0. Another way to show it, and kind of how the book likes to put it, is that the electric field lines are parallel to these four sides of the cube, making them 0, because as we know, this is actually E times ds times cosine of theta. And our normal force here is just pointing straight along parallel with the electric field. So, and this normal force is 90 degrees. And as we know, cosine of 90 is actually 0. So then this ends up being 0. But, so we just have to worry about the top and the bottom of this. The electric field on the bottom is going to be negative E, and then it's going to be times the surface area, or the area just of that bottom part. And then to get the net flux, we have to add that to a positive E here times the area. So ultimately, these E's are going to equal, and the A's are going to equal, so it's just going to end up being 0. So 15, basically none of the dimensions they give us really need to be used, because we can just see that the overall flow is that the electric field flows in and then it flows out, making it 0. So that's all you need to know.